Hello everyone, today we are going to be exploring quantum computers, basically the building blocks, how they work and how we can utilize them, and maybe if you are rich enough someday you can build one for yourself. So first of all we'll talk about classic computers. So we know the classical computers, all the operations in them, they all basically roll back down to bits, which are just switches like on and off, 1 and 0. So I won't be talking much about that. So analogous to that, for quantum computers there are qubits. These are represented by like is equal to some alpha times 0 and beta times 1. So basically what it is it's a superposition. Let's say coin represents head or tail. It's like a 0 or 1. For the duration it's spinning, it represents the superposition. And when you check it out, it collapses to either 0 or 1. And how it collapses is based on the probability. So let's say a qubit is represented by this. We can either say when we check it out, it can maybe become to be a 0 with the probability alpha square, or 1 with the probability beta square. And the sum of those probabilities should add up to 1. Now after qubits, there's also another interesting quality, which is entanglement. So let's say I have a qubit which is in this room and another qubit which is, let's say, in Antarctica. So if they are entangled, when I check out qubit 1, it is possible that the measurement of qubit 2 is directly related to what we get in qubit 1. Let's say our qubit is equal to 1 by root 2, 0, 0 plus 1 by root 2, 0, 1. 1, 0. So for this example, you can just club out the other 0, which can be 1 by root 2, 0 plus 1 into a 0. This is an example of a non-entangled qubit. So here, if you calculate the probability of either getting a 0 or 1 for the first qubit, it doesn't change the result you get for the second qubit. But let's say the qubit was
is everyone comfortable with the notation? It's visible also. थोड़ा बड़ा लिखिए.
ठीक है. Let's say it's either 0, 0 or 1, 1. So when I check out qubit 1, let's say the qubit 1 collapses to 0. So the probability that qubit 2 is 0 is 1, because it only is when qubit 1 is 0. This is an example of an entangled qubits. Einstein called it spooky action at a distance, because it's kind of weird that you're checking a measurement in this room and the measurement in another, let's say, continent is directly related to what you get in this room. So this was kind of weird. So coming to quantum computers, just like how classical computers use normal bits, quantum computers use qubits. And as you can see, these don't directly represent a 0 or 1. It's basically a superposition which can at any time collapse to 0 or 1, and it can represent multiple possibilities. So that's how it helps you kind of do like rapid calculations and vast possibilities in very short amounts of time. This is basically where quantum computers come into place. Now, where quantum computers use? Now, obviously, you won't use a quantum computer to scroll Reddit or watch Netflix, because that's just basically useless. There are basically overheads in quantum computers which keep a track of all the entanglements, all the error minimization, all the superpositions, which is kind of useless for some basic tasks. Now, what quantum computers come into place is when you want to do, let's say, machine learning simulations or
the cryptography.
Yeah, cryptography, molecular simulation. So this is where quantum computers come into place. And now coming to components that quantum computers must have. So first of all, the basic component is qubits, and these qubits must be coherent. Like, it shouldn't be like they just dispose of or get destroyed in just like matter of nanoseconds. That way they will be useless for the duration the algorithm is working on them. So obviously these should be coherent. And analogous to classical computers, we use logic gates like AND, NOR, XOR. Here we use quantum gates. These are also single qubit gates and multiple qubit gates. Single qubit gates, as the name suggests, is applied on a single qubit, and multiple qubit gates are useful for various purposes such as entanglement of multiple qubits. Like if you want to entangle some unentangled qubits, you can use multiple qubit gates. Now, this sphere you see is the representation of Bloch sphere. Here, 0 is represented on the northern pole and 1 is on the southern pole. And all the superposition of the qubits that are possible are represented on the surface of the sphere. And let's say your qubit has some noise in it, so it won't be represented on the surface but rather on the volume inside. And one of the gates is poly gates, which are then again in 3 parts, X, Y and Z. X gate basically what does is it switches the magnitude of the qubit. So if your qubit was a 1, it changes it to a 0. And Z qubit, what it does is it just flips the phase of the qubit. And Y is basically just superposition of X and Z. So first you flip the qubit and then you flip the phase also. Now I'll move it onwards with Ananthan.
So like now you have heard about the basic parts of quantum, which you must have already been aware of. So now what we'll ask the basic question is that what is a quantum computer? So what a quantum computer basically is that it's a computer which uses quantum mechanical effects like the ones which he has explained, like quantum entanglement, to its advantage in order to do all the calculations. So then the next question which comes is that why do we need a quantum computer? So you must have heard of something called Moore's law. Like, Moore's law. So this is like the basic regular computers are made using integrated circuits, and what happens is that Moore's law states like the number of transistors in a specific area of the integrated circuits increases exponentially. So after some time, the size of each transistor becomes so small that quantum effects start taking place in that transistor. So there is a quantum phenomenon known as quantum tunneling. So quantum tunneling basically is such that like small nanoparticles such as an electron can pass through a barrier or a wall through which it is not supposed to pass through. It is like me basically teleporting through this wall. So what happens is that in transistors, this can cause leakage of electrons, which creates a lower limit to the number of transistors which we can have in an integrated circuit. So a solution for this is using this quantum tunneling and other effects to our advantage. That is what quantum computer does. And like you said, like there are encryption algorithms which are practically impossible for present computer systems to solve because it takes such a long time.
Actually, the groupers algorithm basically root the possibilities.
Yeah, so such like that, there are the RSA algorithm, you might know, is one such problem which cannot be solved by the regular computer because a bit has only 2 values, 0 or 1. A qubit can have both these values as that.
Simultaneously have the both values.
Yeah, simultaneously it can have the same value. So what happens is that if there are 2 possibilities, a qubit can represent both the possibilities at the same time. So this can speed up all the calculations exponentially. So this is why we need a quantum computer. We would not need a quantum computer in our daily lives. For such high level calculations, we would be using quantum computers. Next, like as the quantum computer is such a very different design from the regular computer, we will have to design the components also in a very different way. Like regular gates, you might know, like AND or not, these are the regular gates which we use with the bits, but these work on binary values. So in order to have something which works on a non-binary value, which is a superposition of these 2 values, we'll have to make new gates. Like these are very different from the other gates, like the AND or gates. These are the quantum gates. As you can see, the block sphere is just a representation of a qubit. So a qubit means a bit can be represented as 2 values, 0 and 1. A qubit has a lot more values than 0 and 1. The superpositions are there, and other properties of qubits are also there. Like the phase of a qubit is there. Because a bit can be represented as either a circuit which is on or off. So like that, in order to make a physical qubit, what we do is that we take a particular system which has two values. For example, if you take an electron will have two values of spin, -half and +half. So we can consider an electron to be a qubit because it's a quantum system and it has two values, and being a quantum system, it will have a superposition of all these values. So if we have an electron in a specific environment, if you are able to control the electron, we can use it as a qubit. Like that, the different types of qubits are various systems which we can control. So according to those, we have the types of gates also. So means it's like it's a bit of a technical part. It's used in, like, you know, the Grover's algorithm. Grover's algorithm uses some of these gates. Another algorithm which we use is the Dew's algorithm. So there is a problem called a black box problem, which cannot be solved by the classical computers. Means it can be solved. Means the problem basically is that there is a function f of x. So it can have some value. We have two input values of x, 0 or 1. Only two values we are having, and we need to find out whether the function is a constant function or not a constant function. So in order for it to work using a regular computer, we need to give two inputs. So if you are giving 0 and the output is, say, 7, and for 1 also the output is 7, then we can conclude that the function is a constant function. So with the quantum computer, we can do this by one step. We take one qubit, and this qubit will have both 0 and 1 values. So that is the power of a quantum computer. Instead of having two separate calculations, we can do this in
half time. It can even do it in half time instead of performing two operations.
Yeah, exactly. The number of operations reduce, so the time will also reduce. So in this, we use this gate called a Hadamard gate, if you can see. Hadamard gate, basically what it does is that first, in the beginning of each calculation in a quantum computer, we will be initializing the gate, initializing the qubits. The qubits have to be initialized to a specific set of values which depend on the problem. That we will be going to in detail in the end. So after these are initialized, if we want to make it into a superposition, that's what we use the Hadamard gate for. So all this Hadamard gate is the one which we are using in the Dew's algorithm. Like that, there are different types of gates: single qubit gates which act on a single qubit, and multiple qubit gates which involve basically entanglement. Why entanglement is important? It's like if you are having a single qubit, it can have one value. It's a two values. Sorry, it's a superposition of two values. If you are having two entangled qubits, it can have a superposition of all four values. And like that, it exponentially increases. If you are having 8 qubits, it can have a superposition, means 3 qubits, it can have a superposition of 8 values. So this is another important power which a quantum computer is having. With the linearly increasing number of qubits, the number of possibilities which you can check at a time increases exponentially. So this is why we need a quantum computer. Then next we go on to the different designs of quantum computers. So like I said, a qubit is basically a quantum system which has a superposition of two values. Like I said, there are various qualities which a system must have in order to use it as a qubit. Like coherence. Coherence basically means how long the qubit will stay in the quantum state before it gets before the waveform collapses. That is the coherence. And the quantum system we should be able to make this work together in order to have the gates. Like that, there are some properties. So first and most commonly used type of qubits are superconducting qubits. For example, the Eagle quantum computer, which Google has developed, is using this, and then IBM systems, they all mostly focus on superconducting qubits. So what are superconductors? Basically, superconductors are materials which have zero resistivity at some specific conditions. So it will be
of 0.02 Kelvin.
Yeah. At that condition, what happens is that usually they use materials such as niobium and tantalum. These are metals. So what happens is that at such small temperatures, like you said. So what will happen is that the electrons moving through the metal will form pairs. These are known as Cooper pairs. So we are using the properties of these Cooper pairs in superconducting qubits to encode the 0 and 1 values of the qubits. So there are other properties like zero resistivity, and magnetic fields cannot pass inside a superconductor. And there are other, these superconductors are used for lot of there are a lot of applications, like in MRI machine they use. Then what happens that there are three types of superconducting qubits. One is a flux qubit, then there is a phase qubit and a charge qubit. Charge qubits are the most commonly used among these three. And charge qubits, what happens in charge qubits is that there will be a circuit which has a capacitor and something called as a Jefferson junction. So a Jefferson junction is just like a component similar to a capacitor or something. What it has is that this whole circuit will be made up of superconducting material. In that superconducting material, if the wire is coming, superconducting material is coming like this, there will be an insulator in between. So what happens is that the Cooper pairs is that basically pairs of electrons. So the pairs of electrons coming to here will have to tunnel through the insulator. So it's basically based on quantum tunneling. So it acts like a inductor, but it has some nonlinear properties. In first type of charge qubits made of superconductors are known as Cooper pair box. So in that we use the amount of charge inside an area of superconductor as the qubit. If there is a high amount of charge inside the qubit, it will be encoded as 1. If there are no Cooper pairs inside the area, it will be encoded as 0. This is something known as a Cooper pair box. Next one is flux gate. So what happens in flux gate is that there will be a loop of superconducting material, and the direction of charge movement will be considered as say 0 or 1. Means these are quantum systems, so until it is measured we won't be able to find the exact direction. So till we are measuring we won't be able to find. Like you have heard of Schrodinger's cat. That is the basic thought experiment we have to follow here. So I will repeat that basically they have locked a cat inside a box and sent it somewhere. Until you have opened it and checked, you won't know whether it's alive or not. Same situation here. Until you measure it, you will never know whether it's 0 or 1. So there's another type of a subtype of the charge qubits are known as transmon qubits. These are the ones which are commonly used by Google. Google's quantum computers are based on transmon qubits. So what it has basically a capacitor will be there in parallel with the Jefferson junction. So in that what happens is that it is better than a charge qubit in many ways. So these qubits need to be controlled. We need to first initialize them. For that we will be using microwave pulses. We will be supplying microwave pulses to these, and then they start oscillating this is basically forming an LC oscillator circuit. LC oscillator will have a frequency like that, but the difference is that the Jefferson junction creates energy levels. So in order to create a qubit, we will be choosing the bottom two energy levels, and we will be checking the frequency of we will be checking which energy level the circuit is having. If it is having the lower one, it will be 0. If it is having the higher one, it will be 1. And in order to measure this, we will be having something called as a resonance circuit. This circuit will be there, and nearby we will be having a microwave frequency circuit. What happens is that as the electrons are moving through the qubit circuit, the motion of the electron will cause changes in the frequency of the resonance circuit. These changes we will be measuring. So we will be measuring them indirectly. Because if we are measuring directly, the waveform will collapse and we won't be that will cause a permanent.
But I think there is another type of qubit recently discovered by the Microsoft.
Yeah.
For the
Topology.
magic kind of one.
Yes, that we are coming to that. Then what is that? In order to make the single qubit gates, for each type of qubits we are using different mechanisms to make the gates and for controlling analog. So we use the single qubit gates will be implementing using the same microwave pulses. The microwave pulses which we use to initialize the circuit will be using the same pulses to do the calculation. The single qubit calculations will be using. And in order to, if you want to entangle two qubits, what we'll be doing is that we'll be connecting two of these circuits together using a capacitor or an inductor. Or if you want to connect more than two circuits, we'll be using something called a quantum bus. It's a connection using the same superconductor which connects a lot of these. And the problems in these superconducting quantum computers are that they need to be kept at the superconducting temperature, like you said 0.0 Kelvin. Like that we need to keep this, so it's very costly. We won't be able to create such conditions in every lab. That's a problem. And then these are affected by the environment. As it's a quantum phenomena, the environment, the charges going around in the environment will affect this. The charge qubits which we talked about are very sensitive to the charge noise. If we in the same room, if we are running some electrical equipment, that may affect the outcome of these charge qubits. And like that, the environment is the most important thing in these type of qubits. Next one are photonic qubits. So in this we use the properties of photons. Photons have a lot of properties like polarization and frequency, angular momentum, which are having two separate values, and superposition is also available. So in order to do that, first of all we need to have a single photon which we can control. In order to get a single photon, we can use multiple ways like quantum dots. Quantum dots are basically nanoparticles made of semiconductors. They have some special properties like if you are exciting them with a laser pulse, they will emit single photons, and the frequency of the photons you can control by changing the size of the quantum dot. That is one way. Then there is something called down conversion, of spontaneous down conversion of a photon. In that, what happens that the photon of a higher energy will convert into two different photons of smaller energy. We can use this to get photons of our required frequency, and using this we can get the photons, and the initialization can also be done in this way. And what we do is that for this we need a lot of specialized equipment like beam splitters, plane shifter. The equipment which we work with in optics are needed for making these photonic qubits. So that is another problem. The advantages are that we can work them in room temperature. We don't need such cold conditions in order to work these. Then another problem is that we won't be able to implement gates as effectively, because as you know, photons won't interact with each other that much. Photons can interact with matter in a very small ways, but they won't interact with each other at all. So we won't be able to create entanglement of photons to have multiple in order to implement the gates. So that is a problem. And like the photons, as they don't interact with the environment,
Two photons cannot collide. Can they collide or not?
means like we won't be able to get them to interact in the way we want in quantum. Like if we want to have a gate, there are certain types of gates which are useful in the algorithms. We won't be able to get them to interact in that way. So another advantage of the system is that, as we said, the photons won't have much interaction with the environment. So they have a very high coherence state. They will keep their state until we measure them. They won't have much effect from the environment. Then another type of qubit which we have are clapped ion qubits. So in order for that, what we use is that we take an ion of something like calcium or beryllium, and it will be having a single electron, and we will be using the energy levels of that ion as the qubits. Like a lower energy level will be 0 and the higher energy level will be considered as 1 until we measure the position of that lone electron at the means that lone electron will be there, right, in calcium ion Ca+. So the position of that ion will be using as the qubit. So what happens is that we can trap the ion using magnetic fields and electric fields. They are known as pole traps and penning traps. So using these special traps, we can trap the ion in a specific location in order for us to carry out all the gates and the other operations. So the advantages of these are that we can easily get the ions in the place we want, and they won't have that much interaction with the environment as compared to other qubits. But the problem is that we won't be able to control more than one ion in a particular trap. Like the penning trap, what is it like? It is having pole trap. What is happening is that there will be 4 electrodes, and from these the field lines will be going, electric field lines will be going like this, and in the center one atom will be trapped, and these fields will be changing in order to keep the atom in place. So in that we can effectively keep only one ion at a time. So we won't be able to implement multiple ion gates. And like these trap ion qubits are having long.
That will be 1 qubit.
Yeah, this one atom will act as 1 qubit. So we won't be able to keep multiple qubits. We need to entangle them in order to implement the multiple qubit gates. So if you are not able to entangle, then that whole advantage, like I told you earlier, 2 entangled qubits means we are having 4 possibilities. 4 possibilities are superposed together. So that advantage we will lose. So the major advantage is in the superposition. So if we are not able to achieve that, then it's a major disadvantage.
Alright, so till now we have seen about some major methods of using qubits. Another one major method is a neutral atom method. As the name suggests, it's the use of a neutral atom. So basically we'll be using atoms such as mostly alkali atoms are used, like cesium or rubidium. Like as the trapped ion method, the same procedure is used here. The individual atoms are trapped and arranged using light or optical tweezers. So these optical tweezers, they received a Nobel Prize and a recent discovery. And after here also again cooling temperature is required, except they're not as much as the superconductors. Here superconductors usually require a milli-Kelvin levels. Here they require micro levels. Here in neutral atoms, here also there is possible to be for us to be able to implement single qubits as well as multi-qubits. Historically, so it was known that neutral atoms are not as much as effective as a superconducting or other methods. They did not have as much gate fidelity, which means that for us to be able to reduce the errors and to be able to implement complex circuits. But recent discovery has, recently it has been discovered, developments have been made to bring this method in par with the superconducting and the other methods. So the other options that are implemented for making qubits other than superconducting, trap, neutral include quantum dots, NV centers in diamond, and topological. So nitrogen vacancy centers, basically what happens is that in diamonds, as you would have known, in carbon vacancies are removed and nitrogen goes in and gets trapped in them. We use again the photon electrons to remove electrons from them, and then we can use their spin as a property for qubits. But in among all of these things, there is one interesting qubit method that I want to discuss about, which is the topological quantum computers. Any idea anybody has what a topological quantum computer is?
Management one of Microsoft is an example of a topological.
Yes, Microsoft, they released a chip, not an actual topological quantum computer. But do you have any idea what it is actually?
Basically protect the data in some type form of.
a topological quantum computer, instead of using a local particle, like all the other properties that we have seen till now, they use a local particle. The major error that arises was because of the local particle not being able to stay stable in their environment. Like as the previous presenters have told you, they had the noise from the outside, coherency problem, but all of these problems can be solved if we implemented this topological quantum computing. How? Let's see that. So this method, it uses anyons. So like, okay, anyons, another fancy term. Any idea what anyons are? Anybody? So I'll tell you, so anyons are quasi-particles. What is a quasi-particle? Instead of a single local particle, we use a combination of these local particles, and we use a topological itself means using global properties. So we use that. So here the local particles are not as much affected by the external noise or anything. They just depend on the global properties. So we have better coherency, better error analysis, error reduction and all those things. So here I'll explain you what anyons are. So anyons, as I said, are quasi-particles. Their world lines with the braids. So these braids, they triangle around themselves, they braid around themselves to create properties. So here we do not need to make complex circuits for us to be able to implement the quantum properties. Here they are natural. So this is another great achievement we could have had if this was feasible. So again, why this is not feasible? Anyons are 2D arrays. So like, getting a 2D, to be able to have 2D physics is very difficult. To be able to recreate them in labs is very difficult. We need to have like quantum Hall effects, like the semiconductors from the quantum Hall effects. Those are not as feasible. But recently, as one of you pointed out, Microsoft had a research. So in that research, what they presented was the idea of Majorana zero models. So what this means is that these are particles that are antimatters of themselves, and they have zero modes, which means that you do not need external energy for them to excite or do anything. So how these will help, how these change? So these are non-Albanian anions, and these will fasten the achievement of topological by a great extent. So here the Microsoft, what they actually achieved was they used an arsenide semiconductor, narrow wire. They kept that semiconductor very close to an aluminium superconductor, where they observed that one of the end acted as a Majorana zero model, and the other end was an energy gap. They observed that as this energy gap increased, the robustness of the topological quantum computing system also increased, which is a great achievement. And they have recently released a microchip, and this could be a great idea for a research for you guys. And why research on this topic? This is a new recent research, but why do we need to focus on this topic? Is error resilience. As I told, error resilience in topological quantum computing systems are very high, and at the same time you could build large list systems with very less qubits. For example, in the initial methods that we have seen above, like the actual working qubits will be very less, like 1 or 2, and you will need hundreds of other qubits to be able to help reduce the errors in them. But here that's not the case. That qubits will be reduced. Like around 40 to 50 qubits we will be able to achieve something that 200 or 300 qubits would be doing in a superconducting system. But again, still it's not feasible in physical case, because to be able to simulate physical properties, we need around 1000 qubits, and what we have achieved till now is just 100 or 200. You know where the scale is. Next, how do we give binary data as an input to non-binary quantum computers? So we saw that zeros and ones are given as an input. So why they are given is because for qubits we need a superposition to be able to act, and again we don't have those superposition techniques in our hand. So we use what we have, zeros and one binary bits, and we give those inputs for us to be able to get outputs that are desired. So those desired outputs again we get by the properties like the spin or the energy levels or these things that are available in the physical atoms or those things. And quantum advantage, okay, it's a fancy name, but why quantum computing? So one major reason is the ability to do vast number of simulations and great computation power. And all of you guys must have heard, what does this pose a threat to the society? Like quantum computing, what threat does it pose? Any idea?
Confidential data of the other countries, militaries and the rest.
Again, there is a fancy term involved in this, which is
Cryptography.
RSA encryption. Right. So RSA encryptions, they can be easily decoded with this quantum computing. So again, as every scientific research comes out to be, it's a boon and a curse. So that's one thing that can happen. So we would all have to rethink about our WhatsApp messages. It's not safe anymore. And if it's so good, why isn't everybody using it? I mean, it's an obvious answer.
Literally, you know, block that a pair of entangled qubits can exist in 4 states, 8 states, and so on. But a pair of unentangled qubits can also exist in 4 states, 8 states, and so on.
Entanglement essentially means those qubits are linked with each other. Like one property affects the other property.
Yes, essentially, the number of the qubits is not the advantage.
No, no, see.
Advantage is the linkage.
We can, when they are entangled, we can use these 4 states together. We can do the operations on the superposition. These 4 states, when they are entangled, if you are, 2 qubits will be having 0 and 1. 4 will be having 0, 0, 0, 1, 1, 0, 1, 1. These 4 states will be entangled together. The superposition will be there. And if you are having some use case in which we have, like in the black box problem, like you said, there are only 2 possibilities, like say the constant function or not. So in that we had a superposition of two values, and that could be represented as a qubit. So instead of that, if we have some use case in which there are 4 possibilities, we can easily represent them as an entanglement of 2 qubits. That helps us to increase the processing speed, and the number of questions can be reduced.
In this example, like when for the first qubit, if we get a 0, you already know the answer that the second qubit is 0. Now imagine you have like millions of qubits. For let's say 25% of them are entangled. So easily in computation, you can easily see if you're already getting the computation for the first qubit, you can easily map them to the other, which can already be linked to the other. So these like quadruple fold like reduce the computation times by a large amount. So,
Any other doubts? So again, this part discusses about how quantum computing right now is not feasible, because again it requires like cryogenic technology as well, which is like difficult to achieve, and you need billions of dollars for that. And that's why again, which makes topological quantum computing interesting, because it doesn't require that. In the future, like as I was talking about, if we develop quantum computers that are as expensive as the current designs and they work at room temperature, we'll be able to make hybrid quantum computers. That is not just the quantum computing, but also use classical computing, because those two are different things, and we are using both of them, combining both of them to be able to use. Like has great potential in the field of cryptography, cybersecurity. As I said, again, it's like they say it's great potential, but if it comes out, we would have to change everything that we know about cybersecurity. We would have to implement bring out quantum cybersecurity. That is another entirely new research field. So. And there you have it, like you have a solid foundation about the quantum computing, like from the basics, what it is, how this can be made, and what if it comes out. So that's all from our part. Thank you.
If you have any doubts, then you can ask.
Decryption with the maximum number which has actually been practically factored using the RS algorithm is 21, and we need to factor like numbers of the order of 10 raised to 15 and 10 raised to 20 for it to actually hold some practical advantage.
I mean, like the first thing, first research paper on this came out at like 2005, and then the solid thing came out at 2008 by Microsoft. It was a research paper, not an actual quantum computer, and then the other came out at 2025. So you can see the scale.
No, so it's one thing to actually discover a quantum algorithm. Like theoretically, we can discover lots of quantum algorithms.
Already most of them are discovered, but again, you need a quantum computer to use those algorithms.
See, right now the computers developed by Google and IBM have achieved quantum advantage. Quantum advantage means if say the RSA problem, if it is I don't know exact, if it is solvable by a regular computer in say O of n square time, if it is getting solved, a quantum computer will be able to solve it in n times. That is the quantum advantage. That is the like an exponential time-taking process. We can make it into a linearly time-taking process using a quantum computer. That has been already achieved by Google and IBM.
No, but my point is that we haven't actually been able to make those quantum computers which are able to achieve those quantum advantage for actual practical usage.
Actual practical usage
Then
they
from that
have.
actually start to happen, because then only we can actually see some future quantum computers.
Yeah, like we have explained all the problems they are facing, which is preventing the release of quantum computers for regular use. So as soon as these problems get solved, the research is going on in a lot of universities. Not only Google, IBM. If you can see, there are around 300 something prototypes of quantum computers which are already made. 300 something separate entities are working on quantum computers. As soon as any of them find solutions to these problems, we'll of course have quantum computers working in any high level lab.
I mean, right now you also have IBM's cloud like service where you'll be able to use their quantum computers.
It is available in Quick.
Yeah, you can use them.
I mean, it is going to take a lot of time because you have to maintain the perfect condition, like the perfect temperature. There are financial conditions, and the qubits easily get noised. So it's harder to. I see them maybe working around like 25 years or something, but it's still a long way to go.
Again, the whole map of the quantum computers are different from the conventional computers. Like the Q dash language created by Microsoft is much more complex compared to other languages.
Yeah, because the language which we have caters to the bits. Only 2 values are there. But if we have that superposition part, it requires a full rework of the existing even the algorithms are different. So of course, obviously the language will also have to be different in order to work with quantum computers. So this you can see is an article by Penny Lane. Penny Lane is a research organization. So what they have done is that here it's an explanation about the quantum computing, the superconducting. In the end, they have given Python code by which you can simulate a quantum computer in Python. So there are special libraries for this. You can see here Penny Lane libraries are there. This is something which you guys can look into if you are interested.
Whisker has also launched this simulation library.
Yeah, that is also there. Yeah, this is the QuizKit part as you mentioned. So this is by IBM. We have an SDK from this. So this we can use for.
I have already used the Whisker for certain thing I needed to do. At that time, the API function was really open for all. Now they give 500 credit, US credit to 1 person for a month, and that too on a credit card. Unless I will do carding, and that's the.
We can look into it if you want access, maybe then like from the club's resources we can help you get access to it. That doesn't take long. Apart from this, these are some simple programs to get you started on your own laptop. So
The simpler course can be simulated on the conventional computers using the simultaneous.
So what is the concept is that in bits you are using two different states. In qubits you are using a probabilistic model, so there are multiple different states. So to utilize that, IBM has made this particular documentation API calls you can do with this particular SDK is provided. So
after this certain number of qubits, the load of the CPU and GPU will exceed that.
yes, so we have to build our laptops also to go past that limit. So some basic examples are given here with some outputs that you can try on your own laptop maybe. And then if any more resources are required, don't forget to contact us. We can help you get started also in that. So I think that's it from our side.